Alright, welcome back everyone. Today we're going to be continuing taking a look at Z80 machine code for the Sinclair Spectrum and ZX Spectrum Next computer. And the reason I say machine code as opposed to assembly language, because of course we will be taking a look at assembly language instructions as we're learning machine code, but I think it's valuable to learn about machine code before really diving into Z80 assembly language using an assembler, because it allows us to actually learn more in depth about the instructions and how they work, and particularly the codes that are involved and the bytes that are involved in those instructions. So we're going to be taking a look today at how to do some simple instructions. In particular, we're going to be taking a look at how to do a jump, which is a branching operation in our program. And it's going to really demonstrate for us, I think, how valuable and interesting and cool it is to learn about Z80 machine code before we actually learn to use an assembler, which of course we're going to be wanting to use an assembler when we get into creating longer programs later on. But before we do that, I think it's good to start with some foundation work where we learn about machine code instructions, which helps us to learn actually more about the instructions and the bytes of data that make up those instructions. So today we have kind of a fun video. It's going to be a really hands-on video, and we don't need any special environment to do this with. If you have a Sinclair Spectrum computer or a ZX Spectrum Next computer, you can follow along with me if you like, and it's very easy to get started. We're actually going to be using the program that I demonstrated in my last two videos. So if you want to go back and take a look at those two videos, you can load in the program from there. You can copy it from the video description. And in particular today, I'm going to be using just a slightly modified version of our basic loader program that allows us to load in hexadecimal machine code instructions into the computer memory and run it that way. So if you want, you can go ahead and type in the program into your computer, or if you have an editor that you're using like I am, then you can do it that way as well. But it's very easy to get started. And the only note I have to make is that in the YouTube video descriptions, it doesn't allow me to enter the greater than or less than signs in my program. So you'll have to go in and edit those yourself manually. There's only a couple lines where we need to do that. But otherwise, you can just follow along using the program that I provided in my last video, which is a basic hexadecimal machine code byte loader program. And of course, not everyone will be interested in reading this book, but in case you're able to get your hands on it, I find it a very easy read for people who are just starting out learning Z80 assembly language. So if you're able to grab it, then I recommend it. Otherwise, let's go ahead and get started in taking a look at some Z80 machine code. Alright, so let's get started taking a look at this program that I introduced to you in my last video, which is a loader program that allows us to load a hexadecimal machine code program into our Sinclair Spectrum, or in this case ZX Spectrum Next computer. And I'm actually using the Visual Studio Code editor and then some batch files to convert this program for use in the CSpect emulator, which emulates the ZX Spectrum Next computer, as I'm sure most of you probably know. So I'm not going to go through this entire program because I covered that in my last video, but we'll just take a look at the bottom part here where I'm describing the actual program code that we're going to be using today. So what this program is going to do is change the border color on the screen, and it's going to change it first to red and then to blue, and then it's just going to cycle around and keep changing the border color indefinitely. And the reason I want to show this is because it's a good demonstration of what advantages we have by learning machine code as opposed to Z80 assembly language. For example, when we're learning assembly language using an assembler, the assembler does some of the work for us. It does the calculations for us in terms of converting 16-bit values into addresses, and we're able to use some advanced features of the assembler such as labels as well as other assembler directives. But today we're going to start off looking just at pure machine code and really get an understanding of how these instructions work. And you'll be amazed at how good a foundation we're going to get from just this one video, and how much more this will increase our understanding of both machine code and assembly language from just looking at a few instructions. So let's go through the program here and we'll take a look at the information and what it can teach us. So I'll just zoom in a bit here and we can take a look at these instructions really well. And we'll start here at line 5100. So here, if you haven't already taken a look at my last video, you might want to go ahead and do that so you understand how I've laid out the information in my data statements here. So you can see that the data statements start off with a string, which is the assembly language instruction. And then the following byte is a number, which indicates how many bytes of machine code data make up this assembly language instruction. So in this case, this LDA2 instruction is made up of 2 bytes of machine code, which are right here, 3E and 02. So let's take a look at these instructions and see really how we can learn about machine code and what this program is showing us. So as you saw from my last video, you'll already be familiar with how this instruction works to change the border color, but we'll just go through it again. So our first instruction here is LDA, 2, which is a load instruction. So in this case, it's going to load a value of 2 into the A accumulator, which is the A register. And that value of 2 represents the color red on our Sinclair computer. And then let's take a look at the rest of the bytes of data in this instruction now. So here we have our instruction LDA, 2. It contains 2 bytes of machine code data. And those 2 bytes of data are right here, 3E and 02. So in order to understand the machine code version of this instruction, we need to look up what this LDA, 2 instruction is in machine code. And an easy way to do that is you can look in a book, of course, or you can look online. And I'll just show you a website here. Right here we have the website z80-heaven.wiki.com opcode reference chart. And this shows us a lot of Z80 assembly language instructions as well as their corresponding machine codes. So if we take a look here, I'll just go back to my program for a second. And the instruction I'm interested in here is LDA, 2. So if I go back to my instruction sheet right here, I'm looking for LDA. And so I'm just going to actually search for it. So I'll zoom in a bit so we can see these instructions. And if I just search by going Control F, and I type in LDA, and then the numbers on this sheet are represented by the letter X. So I'll put LDA, X, and it comes up with one result there. So here it is here, LDA, X. So to work out the code for this instruction, you go over to the left column here, and you see the first character or the first digit is 3, and then the second character is E. So the code for this LDA, X instruction is 3E, which if we go back to my program now, you can see that's what I have here as my first byte of data, 3E. And then of course we need to indicate the value that we're going to be loading into the A register, which in this case is 2. So that's our next byte of code, which is 02. So our first instruction, LDA, 2, corresponds to the machine code hexadecimal bytes of 3E and 02. So let's take a look at our next instruction now, which is an out instruction. And in this case, it's out FE, A. And the code for out FE, A is D3FE. So the D3 represents the out instruction and the comma A, and the FE represents the port which is involved in this instruction, which is FE right here. So we took a look at this in our last video, so it's not too surprising. And then our next 2 lines of code here, line 5210 and 5220, they do exactly the same thing. They assign a value to the A register. In this case, we're assigning a value of 1, which represents the color blue. And then in line 5220 here, again, we have our out instruction, which will change the border color. So what this program does, it assigns a value to the A register, and then it outputs that value to the port, which changes the border color. Then it assigns a different value to the A register and outputs that new value to the port to change the border to a different color. And then now here comes the interesting part, which is why it's so useful to know about machine code. So what do we want to do after we change the border color? Well, we want to go back and cycle through this program endlessly and just keep jumping back to the beginning and changing the border color between red and blue and going back and forth endlessly. So in order to do that, we need a jump statement, which is not very difficult to understand. We can simply jump to a location in our program. And as you can see here, I've got an instruction that says jump 40,000. And the reason I'm using the address 40,000 is because if you remember from my last video, 40,000 is the value that I've used to initialize this memory variable, which represents the location in memory where our machine code program is being stored. So our machine code bytes are being stored beginning at address 40,000. So that's where I need to run my program from, and that's where the first instruction in my program will live, which is this LDA, 2 instruction. So that's where I want to jump to if I want to repeat this program over and over again. So that's what this instruction in line 5500 here does. It's a jump instruction which jumps to a specific address, in this case 40,000. So now how can we code this instruction into our program here and figure out what hexadecimal bytes we need in order to accomplish this? Well, first we need to figure out what is the code for the jump instruction to begin with. Well, I can go back to my website here, and if I search for it, you can see right here, JPXX is the jump instruction that jumps to a specific memory address, and it has a code of C, and if I look up at the top here, 3 is the second digit. So jump XX has a code of C3 in hexadecimal, and if we look back at my program, that's what I have right here, C3. So that is the jump instruction. Now we need to also enter the address where we want our program to jump to. And how do we figure out what address we need to jump to when it's broken down into its hexadecimal bytes? Because 40,000 is a 2-byte address or a 16-bit address, and we need to break that down into 2 bytes. So that's not very difficult to do. The easiest way to do it is to use a programming calculator, which is exactly what I'm going to do. I'm going to use the programming calculator in Windows, so I'll just bring that over. And it may be difficult to see because it's small, but what I'm going to do is just enter that value of 40,000 as the decimal value. So I'll just enter that here. So now we can see that the address 40,000 corresponds to a hexadecimal address of 9C40. And the way we need to enter it is the low byte always comes first. And in this case, the low byte is 40. So if we take a look at my program again, you can see I've got the value 40 here in my data statement, followed by 9C, which is the high byte of this value 40,000 when it's converted into hexadecimal bytes. So our jump instruction has a code of C3, and then this 40,000 address in decimal gets converted to a hexadecimal 2-byte address of 9C40, but when we enter it into our program, the low byte has to come first, so we reverse those 2 bytes. So here you can see 40 comes first, followed by the 9C. And then finally at line 9000 here we have a final instruction, which is our return instruction, which has a hexadecimal value of C9, which in this case, in this particular program, we don't actually need a return instruction because it will never get executed. The program will never reach this line of code because it's going to cycle continuously back to the beginning all the time, changing the border color. So I just put it there for completeness, just to have a return instruction at the end of my program, although it's not really needed. So let's go ahead and run this program now, and we should see the border color cycle between red and blue. So let's go and do that now. So here we have our emulator, and if I browse to my program, I've just added some functionality to this program to ask me whether or not I want the program to pause and show me each instruction one by one as it gets loaded. So in this case I will select a pause, so I'll say yes. And again, I'll put this program listing in the video description in case you want to copy and paste it into your own editor. And let's go ahead and take a look at this program now. So it says press a key to load machine code program. So I'll go ahead and press a key, and there's our first instruction, load A, 2. So we're loading the value of 2, which corresponds to the color red, into the A register. I'll press a key for the next instruction, which is our out instruction, which actually changes the border color to red, corresponding to the value in the A register. And I'll press a key again. So our next instruction this time is load A, 1. So we're loading a value of 1 into the A register, which corresponds to the color blue. And finally, we have an out instruction which changes the border color again, this time to the color blue. And if I press the key a final time, we have our jump instruction, which tells the computer to jump to address 40,000. And these are our bytes here. C3 is the jump instruction itself, and then the address 40,000 breaks down into the codes 9C40, and we have to enter those backwards. So we have 40 coming first, and then 9C. And then finally we have our return instruction, which will never get executed, but that's okay, we just put it there for completeness anyway. And now let's go ahead and press a key to execute this program and watch the border colors change. So there, it's working exactly as we expected it to work. So I'll just exit out of that now and go back to my program. So here we've learned how to enter the machine code bytes in hexadecimal format to make this program work. Now what I want to do is take a look at that jump instruction, and instead of using an absolute jump to a particular address, we want to change this to a relative jump instruction. And we're going to be able to learn some cool things about machine code by doing this. So here what I want to do is change this JP instruction to JR, which stands for relative jump or jump relative. And when we're using a jump relative instruction, we don't jump to a specific address. Instead, we jump a certain distance, either forwards or backwards. And in this case, we want to jump backwards. But in order to perform a relative jump in machine code, we need to know a couple things. First of all, we need to know where is the program jumping from to begin with, because since it's a relative jump, it's going to be jumping a certain distance from a starting point. So we need to know what that starting point is. And then the second thing we need to know is how to enter that offset value into the computer. So let's take a look at the first question first and figure out what will be our starting point. So let me just change this back to JP. All right, so what we want to do is replace this jump instruction here with a relative jump. And instead of jumping to a particular specific address, in this case 40,000, we're going to do a relative jump, which will jump to an offset relative to a particular starting point. So the first thing we want to do is replace this JP instruction with a JR instruction, which stands for jump relative, and I'll explain how that works in a moment. And then this specific 40,000 address, we're going to be replacing that with an offset value, and we'll do that in a moment as well. So let's see what we can modify from this data line here to prepare for this new jump relative instruction. Well, a jump relative instruction can only jump a certain distance. It can only jump backwards 128 addresses or forwards 127 addresses. So the jump offset is an 8-bit value, so we no longer need 2 bytes to represent a 16-bit specific address. So now I can change this 3 to 2 because the jump relative instruction only takes 2 bytes of data. And so why don't I go ahead and erase this last byte of data here. And so we have 2 bytes of data that we need to modify. So now let's see what we want to do to finish preparing this jump relative instruction. Well, first, why don't we go and take a look at what the code is for a jump relative instruction. So I'll go back to my website here, and if I look up jump relative, we can see it right here, JRX, which jumps a relative offset, and the code for that is 1, 8 in hexadecimal. So we'll go ahead and put that in our program. So we'll replace this C3, which C3 stands for jump. We'll replace it with 1, 8, which is the code for a relative jump. And now we need to figure out how many addresses do we need to jump. Well, before we can figure out how far we need to jump, we need to know where we're starting our jump from. So the way we figure out where we're jumping from is we take a look at what the address of the next instruction would have been after this jump instruction. So our next instruction address would normally be right here where this return instruction is. So we need to figure out what the address of this return instruction would be. And in this case, it's pretty easy to figure out because our program is so short. We know that it starts at address 40,000, and then there's 2 bytes, 2 bytes, 2 bytes, 2 bytes. So we have 2, 4, 6, 8, 10 bytes of program code. And so if we add 10 bytes to 40,000, that's 40,010. So this return instruction here should be at an address of 40,010. And that would be our starting off point for our relative jump, which means in order to jump back to the beginning of our program, which is address 40,000, we need to do a relative jump of minus 10 addresses. And we're going to see exactly how we can figure out a negative number in a moment. So first, what we need to do is finish entering our instruction here. So I'm just going to put jump relative minus 10 like that. And then this 40 here is going to be replaced with a hexadecimal value that represents minus 10. So now we need to figure out how to represent a negative value in hexadecimal. And the way we do that is by learning to use something called two's complement arithmetic. And this is the website that I found. It's called allmath.com/2's-complement.php. And this is actually a converter that converts from values into their two's complement values. So you can use this two's complement calculator on this website to convert numbers if you want. But let's figure out how the two's complement function actually works. So the first thing we need to understand is how to represent a negative number in binary arithmetic. Well, a regular byte contains 8 bits of data, and the least significant bit is on the right, the most significant bit is on the left, and there's a very simple way to tell when a number is negative, which is by looking at the most significant bit. And the rule is, if the most significant bit is turned on, then that binary number is negative. So that's pretty easy to understand. If we have a binary number, let's say this one here, we'll just take a look at this one quickly. You see these green numbers here. This top one is 11001101. So if this is a signed number, we would know that it's negative because the leftmost bit, or the most significant bit, is turned on. So to calculate the two's complement, which will give us the opposite signed value of a number. So for example, if we take the two's complement of a positive number, that will give us the negative version of that number. It says to calculate two's complement without using a calculator, because we don't want to use a calculator, follow the example given below. So the beginning number they're starting off with is 50, which is 0011 0010. And there's a very simple way to figure out the two's complement of a number, which it explains right here. It says convert each of the zeros to 1 and 1 to 0. And this is called the ones complement right here. So that's very easy to do. All we do is take each bit in that byte and we invert it. So if it's a 1, we make it 0. If it's a 0, we make it 1. And that's the ones complement. And that's what they've done right here. You can see that their initial starting value was 0011 0010. And then the ones complement of that is just all of these bits inverted, which is right here. 1100 1101, which is also shown down here in green. 1100 1101, and then we add 1 to that, and that gives us the two's complement. So if we add 1 to this value, then our result would be 1100 1110. So for example, if we have a positive number and we want to figure out the negative version of that number, or the other way around, if we have a negative number and we want to figure out the positive version of that number, all we need to do is invert all of the bits and add 1. So now that we're familiar with two's complement arithmetic, which helps us to figure out the value of a negative number, we know that the number we need to figure out in this case is minus 10, because back at our program here we need to do a relative jump of minus 10 addresses. So the way we can do that is by figuring out the negative value of 10. So we'll start out with a positive value of 10, which is decimal, and the binary value for 10 decimal is 0000 1010. And the way we know that is just by converting our binary bits into their decimal values. In this case, we would have this bit represents a value of 8, and this bit represents a value of 2 in decimal. 8 plus 2 equals 10. Okay, so now, in order to get the negative value of this 10 decimal, we need to figure out its two's complement. And the way we do that is by, first of all, figuring out its ones complement, which is simply inverting all the bits. So here, if we take its ones complement, all we need to do is invert all the bits, or change all the zeros to 1 and change all the ones to 0. So in this case, the solution would be 1111 0101. And then, of course, we need to figure out the two's complement, which is simply the ones complement plus 1. So in this case, if we add 1 to this ones complement value, we get 1111 0110. So this is our two's complement value, which equals minus 10. Right? And now if we want to convert that to hexadecimal, well, we know that 1111 equals F in hexadecimal, and 0110, which is a value of 6, would be also 6 in hexadecimal, just like that. So now this is the value we need to enter into our program, because F6 also equals minus 10 decimal, right? So we'll enter F6 into our program now, right here. So now we have a relative jump that jumps 10 places backwards from the starting point, which is right here where this return instruction would be. So it's going to jump from this instruction back 10 places to the start of the program, which is at address 40,000. So let's go ahead and try that out. And we'll open it in our emulator right here. And I'll press no because we don't need it to pause. We'll just go ahead and let it load the entire program for us. And here you can see, if we look at it, well, it's paused because the screen is full. Here we have our load a, 2 instruction, and then our out instruction, our load a, 1 instruction, our out instruction, and then here's our relative jump instruction, which takes 2 bytes, 18 and F6, and then we have finally our return instruction, which won't actually get executed because this program loops continuously. But now, instead of executing this program in our emulator here now, what I'm going to do is show you a function of the CSpect emulator, which is really cool, especially if we're doing machine code and assembly language programming, which is the debugger function. So I'm going to enter the debugger now by pressing F1 on my keyboard. And here we are in the debugger. And this is really cool. It has some interesting stuff that it shows us on the screen here. In the top left part of the screen, it shows us the disassembly of our program, which indicates all of our assembly language instructions. Then on the bottom, we have the memory addresses that show us all the data that's contained in the memory of our computer. On the top right here, we have the registers and the flags. And then finally on the bottom right, we have the actual output from our emulator. So we have our little emulator screen down there. So now what we want to do is take a look at our program in memory in our debugger. And the way we're going to do that is we're going to go down here and we're going to type G, which stands for go to, and then I want to go to the beginning of our program, which is at address 40,000 decimal. So if I type in 40,000 and press enter, you can see the output window here has changed now, and it has a starting address of 9C40 in hex. And if we look at our calculator again, we can see that 9C40 equals a decimal value of 40,000, which is the beginning of our program. And if we take a look at the instructions here, we can see here's our load A instruction, 2, which loads A with a value of 2, which represents the red color. And then we have our out instruction, which changes the border color to red. Then we have our load A, 1 instruction, which will load the value of 1, representing the color blue. We have another out instruction, which will change the border color to blue. And then here we have our relative jump instruction. And let's take a look at it to see if we entered it correctly. So here you can see it's jumping to an address of 9C40. So although this is a relative jump, it's showing us here in the disassembly window the actual specific address that it's going to be jumping to, since it's already calculated that relative offset for us. And the address it's going to jump to in this case is 9C40. Even though we entered an offset, it converted it to a specific address for us. And this address is 9C40, which is right up here at the beginning of the program, which is exactly where we want it to jump to. So it looks like we've entered our jump relative offset correctly. And then finally down here we have our return instruction, which won't ever get executed. So what we can do is, you can see over here the program counter register, which indicates where the next instruction that's going to be executed is. Here it's pointing to some random address. So I want to change that program counter to point at the beginning of our program, which is the address 40,000. And the way I do that is I simply enter PC down here and then 40,000. Like that. And now you can see the program counter has changed to a value of 9C40, which equals the starting address of our program, 9C40, which as we know represents the address of 40,000. So now let's go ahead and we can press the F7 key to step through these instructions one by one, and we'll just watch it work. So we can see now if I press F7, it's first of all going to execute this first instruction, load A, 2, and we can see over here our A register now contains a value of 3. So if I press F7, our A register now contains a value of 2, which is exactly what we expect. And now we have our out instruction, which should change the border color to red, which it does. You can see our output down here, the border has changed to red. And now if I step to the next instruction, we're going to load A with a value of 1, which it does right here. A has a value of 1 now. And again, our out instruction will change the border color to blue now, which it did. And then now we have our jump relative instruction, which should bring our program execution back up to the beginning at address 9C40 here. So when I press F7 now to step through this instruction, we can see our program counter has changed to 9C40, which is back at the beginning of our program. And as I press F7 over and over again, it just cycles through these instructions, changing the border color and cycling from red to blue and back again endlessly. So now let's exit the emulator and run this program again and watch it operate with our relative jump instruction. Alright, here's our emulator. We'll load the program up. Now press any key to execute the machine code, so let's go ahead and do that, and we should watch the border change from red to blue just as it did before, except this time it will do it using a relative jump instead of a specific jump. So there we go, our border is changing colors now, and if we want to maybe change the values, I can change, let's say, this red color. What if I change that to green, which is number 4, and I'll change it over here as well. And then maybe I'll change this blue color to yellow, which is color number 6. Now we should see our border have different colors now when we run this. And now our border is cycling between green and yellow. So that's just how easy it is to modify a machine code program in this little loader program that we set up in our last video. And it's a really good introduction, I think, to get started learning about machine code and assembly language instructions and really become familiar with how the bytes in those codes work. And we can see exactly how those bytes get stored in memory. So there we have a brief introduction to machine code and some assembly language instructions. And I think it's really interesting to learn about the machine code versions of these assembly language instructions before we really start relying on an assembler and the assembler directives and all the cool features that offers us. Because once we have a good foundation of machine code and the machine code language instructions, we can really have a good understanding of how the data in our program is stored in memory and what it's actually doing. So hopefully you found this video interesting. Thanks again for watching, and as always, we'll see you next time.